to account for all of that, and since hydrogen and oxygen come in a 2-to-1 ratio, it means we're only going to make half a mole of water. So we'd have to list the other half a mole of oxygen as still left over. They didn't just go, right? We also didn't just into existence a whole bunch of hydrogen to make a full mole of water. So we have to balance our equation so that everything we start with equals everything we end with. Even though we might have way more or way fewer molecules, we should have the same number of atoms always accounted for on both sides.
Okay, so it always has to be
Balanced.
balanced.
Equal is not correct. Balanced is a much better word to use. And that is the word that we will use once we get much later in this chapter. Follow?
Yes.
There was a question, I don't remember who asked it, about why beryllium doesn't form an ionic state when we were looking at our ions and ionic states for compounds and ionic molecules, remember? Back in chapter 4? And the reason for that, which makes a lot of sense, beryllium is in our second period down there. And something interesting about beryllium, to a degree of information that we are not being held responsible for by this textbook. But remember that first guy, how many books can fit on that first shelf before it's full? We're going previous to this chapter to answer a question from a previous class. 2, right? So, in order for that first shelf to be full, hydrogen, it only needs 2, right? Now, when we get to that second shelf, that second period of elements, that can hold a total of 8. But what we're not telling you, because we're just keeping things nice and simple for this degree of detail for this class, is that actually it's not 8, it's 6 plus 2. That 2 is the same thing that hydrogen has back there, the same thing that helium has back there up on the top. So we have 2 plus 6. That's 8, so we just say 8, right? The reason that beryllium doesn't form a nice ion is because, well, with 2 electrons, it fills up the first 2 slots of that 2 plus 6 nice and even. And so it's really hard to rip an electron out of that mini shelf, if you will, that first portion of that shelf. So its energy of ionization is very, very high. So high, in fact, that for the discussions and considerations of the rest of this book, we assume that it's not actually going to form any ionic compounds, because it's just that hard to rip an electron away from beryllium. It is possible, just like it is possible to fix nitrogen and break that triple bond, but it's just hard. So that's why it was not part of the ionic tables of either the easy ones to calculate or the odd ones to calculate, because they have multiple ionic states. Wasn't sure about that, but as soon as I looked it up, I was like, that makes perfect sense. All right, so here's our conversions so that we can use this in math. What type of math can we use this for? Well, if I give you a certain, later on we're going to learn about the relationship between the weight of an atom and a mole. So if I asked you how many moles there are in this many grams of a compound, or if I asked you how many atoms of sodium were in this many grams of salt, you could figure that out. You could take the number of grams of salt that we have, figure out the weight per mole, figure that out, and then calculate how many particles you have in that 1 mole, and then tell me that there are 10,460,000 or however many there happens to be in that particular question. This is no different than 2.2 pounds in 1 kilogram, that type of thing, right? Or 1 inch in 2.54 centimeters. With the exception that both of these are exact numbers. That should mean something to you, by the way. Both of these being exact numbers. So, as an example, we have half a mole of carbon dioxide. We want to know how many molecules are in half a mole of carbon dioxide. By the way, somebody tell me what's happening here again? We have solid carbon dioxide, CO2 in the solid state. Something is occurring to shift it directly into CO2 in the gaseous state. What did we call that again? Sublimation. Sublimation, right? We did not talk about the math required for that because it brought entropy into the room, and we're avoiding entropy, at least in the mathematical sense, right? So, we need this. Can you already tell me, because we already did this, before we get to the answer, how do we find out how many particles, how many molecules are in half a mole of CO2? Take Avogadro's number and do what? Divide by 0.5, right? Or multiply by 0.5, divide by 2. Moles of CO2 using Avogadro's number. 1 mole of CO2 is 6.02 times 10 to the 23rd. 0.5 moles times that equation, molecules per mole, and we get 3.01 times 10 to the 23rd. That sound familiar? From the off-the-cuff question I asked you earlier? Does sound familiar, right? Just double checking. No? Completely don't forget. Like I said, we flushed everything from the first test.
Correct.
Well, a little bit of studying, reviewing it all. There we go. So, moles of elements. As I discussed before, here's a molecule of aspirin. We have 9 atoms of carbon in this molecule. We have 8 atoms of hydrogen, the little white dots. Carbon's the black ones. We have 4 atoms of oxygen in this molecule, the slightly larger red dots. Why are the white dots smaller than the black dots? What's that? It's not, well, yes, the mass is different between hydrogen and carbon.
You only have one shell.
Right, hydrogen only has one shelf, only one outer shell, right? Carbon is on that second period, so it has 2 shells, so it's going to be bigger. The diameter of the atom will be larger, right? That's why the white dots are a little bit thinner in diameter than the black dots or the red dots, right? So this is our stick model, stick and fill model, where we have our atoms, but we're still representing our bonds. Do you see the difference? Do you see the double bonds in this picture? We talked about single bonds and double bonds and triple bonds, right? Do you see the double bonds that are represented here? So by way of questions that perhaps some of you recently saw, I would be able to ask you about the shape of different portions of this molecule, right? Based on how many bonds we have and therefore what bond angles they would take, this is all review for us now, right? I hear it. Almost gleeful laugh. That warms the subcockles of my heart.
No, it was the incredulous laugh.
Oh, incredulous laugh. They're easy to confuse. So, the subscripts here in our atomic formula are showing you the ratio of the atoms that it takes in order to make up that molecule. C9H8O4. 9 atoms of carbon, 8 atoms of hydrogen, 4 atoms of oxygen. If you combine all of those together in molar ratios instead of atomic ratios, it takes 9 moles of carbon, 8 moles of hydrogen, 4 moles of oxygen in order to make 1 mole of aspirin. Which once again would have how many molecules in that mole? What's that magical number that you could just look up, but we're going to say it over and over. 6.02, you can throw a 2. We should probably just go 6.02, because that's what the book says. So the questions and the homework are going to be related to 6.02. If you look up Avogadro's number on Wikipedia, it goes beyond 6.02. Not too much further. It's not like pi that just goes on forever. Literally forever. 9 moles of carbon per 1 mole in aspirin, 8 moles of hydrogen per 1 mole, 4 moles of oxygen per 1 mole. These are conversion factors that we could use to determine how many moles of carbon are in a certain fractional weight. 1 mole of aspirin, 2 moles of aspirin, 7.314692 moles of aspirin. Right? A little bit of math, and you can tell me exactly how many particles that is, right? All right, molar mass. This is what I inferred via my questions that were well before we got to the information at the beginning of class. How many, take a guess, don't read the slide, take a guess, how much, what do you think a mole of sodium weighs? Or you can just read the slide, because you probably already did. A mole of sodium weighs 22.99 grams. Okay, now, where did we get that number? Did we divine it from a crystal ball? Did we ask someone to come by with a Y-shaped stick and find enough water until we're no longer thirsty that we could actually think about the question? How did we come up with this number? We look over at sodium over there. We can't really see it because the light's off. The atomic mass of this atom, right? Not the atomic number, the atomic mass. Why is it 22.99? Why not 22 or 23? Because remember, you will never, ever, 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 ever find an atom of sodium that weighs 22.99 atomic mass units. Why would 1 mole of sodium weigh 22.99 grams then? Because remember, that weight right there is the ratio of all of the different, what's the name for things that have a different number of neutrons? It's the same number of protons and electrons? Isotopes. That is the ratio of all of the different isotopes and their fractional representation to give us the average weight. And so if we get 6.02 times 10 to the 23rd atoms of sodium, you think we're probably going to be right around, right like on the nose of what that average actually is. If I flip a coin, 6.022 times 10 to the 23rd times, what percentage of them are going to be heads? 50%, right? If I flip it once, it might be 0 or 100, right? The more we the larger the sample, the closer we're going to get to that exact average. 6.02 times 10 to the 23rd is a lot. It is, in fact, so much that it is beyond most studies, what most studies have found the human mind is capable of actually perceiving. Which is why we can talk about the US debt being in trillions of dollars and not just freak out. Because it's so big that we're like, that sounds like a lot, it'll take us a while. Like if somebody said, go find me 600 apples, you'd be like, well that's gonna, I could do that, but I'm gonna need like multiple trucks. Like you can picture 600 apples and it's not gonna break your brain. 6.02 times 10 to the 23rd, but it takes that many atoms to get to a reasonable weight. In fact, to get to exactly the weight of the atom itself, except in grams instead of atomic mass units. Molar mass of 1 mole of carbon, therefore, is what? 12.01 grams. Chlorine's molar mass is 35.4527. So what's the weight of a mole of chlorine going to be? 35 point whatever I just said. Because our memories are sharp, right? That is true of everything on this periodic table. We can pull out silver, we can pull out carbon, we can pull out sulfur. The weight of a mole is going to be the atomic mass. The molar mass to the 100th place, or at least 4 significant figures. This is giving you molar quantities, but not with respect to weight anymore, but with respect to volume. So here we have 1 mole of sulfur, that's not a lot, but 1 mole of iron looks like even less. 1 mole of sodium chloride, 1 mole of whatever that is, 1 mole of C12H22O11. Why is it taking up so much more space? How many atoms do we have in this compound? 12 plus 22 is carry the 5, right? So we've got a lot more atoms in this compound right here than we do in sulfur or iron, right? So if we're combining that many more atoms to make one compound, even though this is still just 1 mole, that molecule is sizably larger than an atom of iron, wouldn't you say? Therefore, it would make sense that it would take up a sizably larger volume. Because a mole is an exact number of particles, molecules, not by weight, but we can use it to determine the weight. Could you tell me the weight of in grams of this molecule? If I gave you a calculator and a little bit more light, how would you do it? Well, what's the weight of a mole of carbon? Where would you find that? underneath the C on the periodic table, right? What would you multiply that by? 12, because there are 12 of them. What's the weight of hydrogen? You'd look that up over there, and then you'd multiply it by 22 and add it to the first number. What's the weight of oxygen? You'd look it up and multiply it by 11. And we would do all of that to 4 significant digits, and that would be our answer, right? What's the molar mass of lithium carbonate? 2 atoms of lithium, 1 atom of carbon, and 3 atoms of oxygen for every molecule. So if we want to know the molar mass, we have to do exactly what I just said, except for different elements. So lithium is 6.941, carbon is 12.01, oxygen is 16.00 in this. Because for whatever reason they're round, well, it's because what? Okay, that's a good question. We're using 16.00 here as grams of oxygen for the molar mass of oxygen. When we look over there, we got 15.9994. Why didn't we use 15.9994? Why didn't we use 15.99? We're supposed to use whatever's up there to 4 significant digits. So why does that turn into 16.00? Because of rounding. Because whenever we talk about significant digits, if we have anything past that, what do we do with that 5th number that we are not supposed to count anymore? We round. So 16.999 or 15.999 becomes 16.00, right? Still 4 significant digits, not just 16. Because how many significant digits would that be? Just 2. We want 4. We can then take those numbers there, multiply it by the number of atoms we have in the molecule, or the number of moles it would take to get a mole of that molecule. So 2 for lithium, 1 for carbon, 3 for oxygen. These are our numbers, and then what would we do with those 3 numbers? We would add them together. And how many decimal points would that new number be? 2. Because we have 2 in each one of these numbers, right? And we know from our understanding of significant figures that we maintain the least number of decimal places out of all of the options. Conveniently enough, we have 2 in everything here, so 73.89. Does everyone feel confident that you could do that with any other molecule I want? Pretty simple, right? Where would you find the weight of the individual atoms in that molecule? Right over there. Or, if you have the book, right, oh darn, there. Or, if you have the interwebs, a series of connected tubes, from what I've been told, you might be able to find a myriad of examples. Up to and just go into Wikipedia and it'll tell you the individual elemental thing for carbon, and I'll tell you all the things. Periodic table is the easiest place to go. Hmm. 7.3. Use molar mass to convert between grams and moles. Can you already guess what we're going to do here? Can you get ahead of the slides? So we now know how to calculate the number of moles of an atom. So how could we convert that to grams? Do we already have those conversions in our head? Have we already been talking about them? We just haven't written them out? Actually, we have written them out once.
In that previous slide, how did we only have 2 sig figs?
There's 4 sig figs there. We have only 2 decimal points.
Oh, okay. That's... Thank you.
Okay. We can get the molar mass in grams, because how many grams per mole is there in oxygen? 4 significant figures, 16.00, right? So we could take the gram calculations, get them out, and we have this. What's 1 mole of carbon, or excuse me, 1 mole of carbon plus 4 moles of hydrogen, otherwise known as methane? What's 1 mole of that weighs? 16.05 grams. That is our molar mass. The weight label on this Morton salt tells us that we have 737 grams of sodium chloride. Could you tell me how many moles are in that? How would you do it? Sodium chloride is conveniently giving us our ionic compound, which we know from previous nomenclature and otherwise that is a 1-to-1 ratio, right? If it was something other than that, considering the way this is drawn, it would tell us because it would be Na2Cl or whatever, right? So this is a 1-to-1 ratio. Can we find the weight of a mole of sodium by looking at the periodic table? Yes. We can do the same thing with chlorine. So we can find out how many grams a mole of sodium chloride would make, would take, would have, right? And then we just divide that by that much. How much do you think it is? Ballpark it. Chlorine's about 35. Sodium's 23-ish. So we're looking at 58 grams. So just under 2 per 100. So we're looking at 14, just around 14 moles. Let's see if we're right. Given this, we need the moles of this. We want to connect the molar mass in order to do the equations. So what do we have? 1 times 22.99 plus 1 times 35.45. That's 58.44 grams per mole. These are our conversion factors. We can plug either of them in, but we will use the one that will give us the correct answer. So we use moles of sodium chloride because that way we can cancel out grams of sodium chloride here with grams of sodium chloride underneath, right? This is just chapter 2 over and over and over and over again. I warned you guys this back at the beginning, right? This stuff does stick around. It is cumulative in the convenient way as opposed to the annoying way. Actually, it's probably cumulative in the annoying way because it means you actually do have to remember it, as opposed to just really cramming for a cumulative test at the end of the semester. 12.6, so less than 14. Question! Why 12.6? Why not 12.62 or 5.8? I'm hearing some mumblings. A little more confidently. How many significant figures do we have right here? 3, which means our answer can only have 3. Good! I'm confident that you knew that because I've looked at all of your grades for the first test. A fluke? I hope not. I hope it's not a fluke.
I don't know, I got my grade back. I'm like, are you sure?
Are you sure? I'm not going to check. Remember what I told you guys. If you go back, this is the first time I've run through these with these questions. So it is possible that you got something wrong because of my mistake instead of yours. So if you want to maybe improve your grade, you have a week. I should have put that in the syllabus. I don't think I did. You have a week to look at your grades and get back to me. And if I think I shouldn't have missed question 12, I can go in and look at your question 12, and if you're right, then I will give you the point back. I will give you that point.
I haven't seen it.
It should, it's there, it's there. No, because it doesn't close till Thursday. I can close that out for you, and then...
Like the first homework. Because I've been trying to look at it.
Yeah.
I may have.
This is that same problem, isn't it? All right, then we're going to make our first exam be an arbitrary amount of time for a week from whenever we figure out how to make this happen.
Okay.
And I'm posting a tutorial now to help
It's not
you.
the exam, it's just...
No, it's all of them. Which
Well,
do
yeah.
you know how to do it? To
I
look
just
at the
wanna look
individual
at it.
questions?
No, Michelle does.
No.
Well, it was sort of. We were looking for it earlier, and I may not have enabled it. I'm not sure.
I think you need to enable it, the submission view.
Yeah, and
Yeah,
we'll work on that after class.
You have
But
to close the exam and then you have to enable the submission
Right.
view.
so when I have done that,
A week from then.
we'll have a week from then. Because, yeah, like I said, I'm not here to punish you guys. I'm here to help you learn. So, you can go in, once we've enabled the ability, go in, look at your exam. If you missed question 12 and you don't think you should have, don't just email me and say, why did I miss all of these questions? Look at them, do them again, find out, and if to the best of your knowledge you did it right, and there is no other answer that is correct, it's entirely possible that when I was taking these guys in, I did something wrong. So,
She's saying we have an extra week to think that we failed.
no, you have an extra week to think that you might have gotten a better A, or instead of the slightly less better A.
Oh,
Like, 85 and up is an A so far, right? So most everybody's right on that border between a B and an A with respect to their exam grades. I know, did we not do the math in the syllabus when we got the syllabus? Oh yeah, the first 45 minutes of the first day, I know, just go like that. It's all a blur in my head too. So, here we have a nice flow chart, so we can go from mass of something to moles of something to particles of something, and back and forth, and any and all of it. I don't know if this is an informative page for you guys or not. It really depends on how much you like flow charts. If you love flow charts, this page is awesome. If you don't, it's just summarizing everything we've talked about so far. Summaries are good too. 7.4. Here's where we get into balancing equations. What is the difference between a chemical change and a physical change?
One changes appearance, one changes makeup. Changes physical properties.
There we go.
Okay.
One changes the chemical properties of a substance. Which one is that?
Chemical.
The chemical change. A physical change changes the state, right? It can be a change of something about it, but it's not going to change the chemical properties. The conductivity of gold is the same as a bar as it is as a foil, right? But if we take that gold and combine it with something else, the conductivity will change. It might go up, it might go down, but it will change. The chemical properties are changed by chemical reactions, chemical changes. So if we take pure silver and or silver sulfide, we are going to have different properties to those two compounds. Could you tell me what one of those different physical properties is going to be just by looking at this perhaps poorly lit picture of a silver and silver sulfide spoon? Fork. That down here, the pure silver, that looks awful shiny, doesn't it? This up here looks kind of dull and yellow. Different chemicals will have different chemical properties because of the atoms that make them up. In the same way that different atoms have different chemical properties because of the protons, neutrons, and electrons that make them up, right? The recipe matters. What's the difference between iron and iron oxide? Which brings us back to the really bad biology joke that I blew when I tried to tell it to you. Why is your blood red? Because it's rusty. Your blood is red because of the iron in your hemoglobin that picks up oxygen, and iron oxide is red. Fe2O3. You remember how to do the calculations for that, right? Mm-hmm. So, when we write a chemical equation, what we're doing is we're listing all of the atoms and the molecules that it takes to react together in order to form the products of that reaction. But remember, we cannot either create nor destroy atoms, which means when we're talking about the ratio of these atoms, we have to balance that out. We cannot invent hydrogen, or in this case, carbon or oxygen atoms. So is this equation right here already balanced? Do we have the same number of carbon atoms on the left as we do on the right of that nifty little arrow with the delta in front of it, indicating that there is some change going on there? In this case, delta E, which is actually energy. How do you know that there's energy being released in this reaction? The picture gives you a clue. Heat. That nice warm color coming off of that.
And light.
Color and light. Color is light. So, is this reaction, is this equation balanced? Do we have the same number of carbon on both sides? Do we have the same number of atoms of oxygen on both sides? 1C, 1C, 2 oxygens here, 2 oxygens there. Now, we did have a change of state in here as well. Carbon is a solid when we are beginning. Oxygen is a gas. Do we have to worry about that? No. What we have to worry about is how many atoms we have. The state of that carbon dioxide is going to be determined by the starting points of those two molecules. The natural state of those atoms, of that molecule, at the energy level that it is created. Question?
So what's the S energy?
The S is for solid, for carbon, because it's
Okay.
briquettes. And the G is for oxygen, because it's a gas.
Oh, okay.
And so what would it be if either one of those was a liquid? We've seen it before, but maybe I just didn't point at it and make sure everybody saw L, right? Sometimes, especially if you're talking about solutions, ionic solutions, you might see an abbreviation AQ. Anybody want to take a guess what that means? Aqueous, so in water, right?
Are those going to be important when we're writing up these equations to balance them?
For balancing, no.
Or are they going to be important?
Later chapters, maybe.
Like which ones? Very specific.
Not very well. With respect to this chapter, we're not going to have to worry about it. When you're balancing an equation, we're going to worry about whether physical carbon or physical carbon. What matters is it there or not, right? If we were talking about entropy and a delta G, so free energy exchange, so when we start talking about whether or not things are exothermic or endothermic under different conditions, so whether or not they require heat, i.e. when you were in chemistry lab you added the Bunsen burner, or if they gave off heat, i.e. you didn't add the Bunsen burner and your teacher said, no, don't touch this. Question?
Well, you said you don't really know, I guess, when this will come up in later chapters?
Not which one specifically, but would you note that down? He said number 12. Be extra careful when we get to chapter 12.
Okay.
We're not worrying about entropy. If we were worrying about entropy with respect to delta G in this chapter, then yes, a change from a solid to a gas would matter. But we're not worried about that right now, because I'm not going to give you an equation to balance that can't happen.
I'm just thinking of examples.
Yeah.
Great.
Yeah, I can see why that would be a concern. You're thinking of that because we just finished talking about change of state and how that's a calculable thing, right?
Mm-hmm.
Right. And if that becomes an issue, we'll be talking about, we will have tables that give you the amount of energy it takes to have the change of state between solid to gas for carbon or whatever molecule it is that we're dealing with. Because that equation would be very similar, yes. How much energy does it take to do this? Yeah. It's pretty much the same equation. If not exactly the same equation, but just with different numbers, because it's different compounds, with different physical properties, because it's a different chemical. So, to write a chemical equation, lots of words. We're going to write all of our reactants, the things that are combining on the left side. Reactants react to make products. Products are the product of a reaction. So since we like to read left to right, we're going to put our reactants on the left, products on the right. The delta sign here over the arrow indicates that heat is used to start the reaction. There are exothermic reactions that mean the reaction will happen and it will give off heat, just by way of referencing them. It doesn't matter how many reactants we have to list or how many products we have to list. We should denote the state of them as either solids, liquids, gases, or aqueous solutions. Here's everything we just said, but in table format. So, in the balanced chemical equation, we have the same number of atoms, and or you can use the term mole interchangeably with atoms, because remember, a mole is an exact conversion between mole and atoms, right? So we have 2 moles of hydrogen gas, which means we have how many moles of hydrogen atoms? 2 moles of hydrogen gas, but hydrogen gas is 2 hydrogen atoms each, right? So 4. We're combining them with 1 mole of oxygen as a gas, but that is how many moles of oxygen atoms? So, thus we have these 4 hydrogens written down here, these 2 oxygens written down here. These guys will combine via multiple steps that we are summarizing here to form hydrogen and oxygen as a molecule that we call water, H2O. 2 moles of water, which has how many atoms of hydrogen? 2 times 2 is 4. 2 moles of water have how many atoms of oxygen? 2. So we have the same number of hydrogen atoms and oxygen atoms on both sides of the arrow, right? And so therefore this equation is balanced. True? True. So let's write an equation using the correct formula for reactants and products. So here we have aluminum plus sulfur, both as solids, are reacting to form aluminum sulfide with this ratio of atoms. If I wanted to, I could ask you the full name of that ionic compound, right? You can figure out what's going on here. What is the full name of that ionic compound, and is that a trick question? Anytime somebody asks you if that's a trick question, it probably implies that that's a trick question. It's aluminum sulfide. Why? How many ionic states can aluminum be in?
2.
If it could be in 2, then we would have to worry about what ionic state it was in, and it wouldn't be aluminum sulfide, it'd be aluminum 3 sulfide, or well, in this case, aluminum 3 sulfide, right? But aluminum can only be in 1 ionic state when it's forming compounds, because it was on that short list of easy to remember guys, right? As opposed to the hard to remember guys, the troublemakers, like iron.
Is there aluminum sulfate?
Sulfate, yeah, but that's very different than aluminum sulfide. This is aluminum sulfide. Aluminum sulfate would be AlSO4? Yes. Okay. Sulfate as opposed to sulfite, hyposulfite, right? Remember the polyatomic ions? So, on the reactant side, we have 1 atom of aluminum and 1 atom of sulfur. Let's go back to the equation. On the reactant side over here, we have 1 atom of aluminum and 1 atom of sulfur. What does that form? 1 molecule of aluminum sulfide. All of these are solids, which for currently doesn't really matter, but we should still write them down. So, is this balanced? Currently? No. We only have 1 aluminum on the left, and how many do we have on the right? 2. Thus, the unbalanced in bright red in this table. We have 2 atoms of aluminum on the right, 3 atoms of sulfur on the right. So what do we need to do to balance this? We need to make the ones on the left equal to the ones on the right. So, what's an easy way to do that? Just take these numbers right here and put them over here. Then we would have the same number of atoms on the left and the right, right? What did they do to answer that? They took the numbers right here and put them right here. 2 aluminum atoms plus 3 sulfur atoms. How many moles of atoms do we have on the left of this equation now? 5. 2 plus 3. How many moles of atoms do we have on the right in the products of this equation? We have 5 moles of atoms. How many moles of products do we have? 1. What's the number that we didn't write here because we don't bother to write a 1?
You just answered your own question.
Yes, I did. 1. Why is it that we didn't write 1 right here and 1 right there? Because you don't write 1 when there's just 1, right? So there is 1 mole of aluminum sulfide here. Yes, there are 5 atoms, or 5 moles of atoms in it, but there is still 1 and only 1 mole of aluminum sulfide compound, the product aluminum sulfide, on the right-hand side of this reaction. Was that an almost question, hand gesture?
Yeah, it just brought back memories of high school chemistry.
Well, that's good. Dredge it up, unearth those gems of knowledge. All right, here's where things get tricky. Let's balance some equations with polyatomic ions. Here we have sodium phosphate in an aqueous solution combining with magnesium chloride in an aqueous solution to form magnesium phosphate and sodium chloride. That magnesium phosphate's a solid. Note how we have an S here. That's why in this little thing back here, we have an aqueous solution combining with, it's kind of hard to tell from the picture, but there's a little dropper of another aqueous solution. But when those two solutions mix, we get this of a solid that wasn't there before. Cloudiness floating around. And if we let it sit long enough, that cloudiness would all down in the bottom. If we centrifuged it, the same process would happen, just a lot faster. Where is that solid coming from? That solid is a combination of magnesium and phosphate. Our sodium phosphate is aqueous, which means it's just dissolved in water as ions, right? Here we have magnesium chloride, that is also aqueous, which means it's just dissolved in water as ions. But when we combine all four of these things in an aqueous solution, magnesium phosphate does not dissolve easily in water, and so therefore it precipitates. It becomes a solid. Individual little atoms that are no longer fitting in between the molecules of water, and so we can see them as a solid precipitate. And then, of course, sodium chloride, which is aqueous, right? So, how do we balance this? Too many variables. Head imploding. Okay. Well, let's not get too worried. First off, here's something to look at. We can make this easier on ourselves by defining our units. So yes, we have a lot of atoms here, right? But does that phosphate and sodium phosphate change from our products to our reactants?
No.
No, it's still PO4, right? So we can treat that phosphate as one polyatomic ion instead of one phosphate and four oxygens. And if we maintain a balance, if we have just as many phosphates on the left as we have on the right, then will our phosphoruses, our P's, be balanced? Will our oxygens be balanced? Yeah. At least with respect to those guys, right? In this case, it's the only place we find oxygen, and so it'll be balanced too. This is why we have that PO4 in red down here, and the PO4 in red, orange, whatever color is entering your eyes, down here. It is not balanced. What's the first and easiest way to see that?
It says unbalanced underneath.
Okay, what's the second and next easiest way to see that? What's the first thing that you run into? Sodium. How many of sodiums are on the left? 3. How many on the right? 1. Not balanced. So, the reactants does not equal the products, therefore unbalanced. Notice we are not listing individual atoms of phosphorus, nor individual atoms of oxygen here. We are listing that polyatomic ion, because it does not change between the products and reactants. So if we balance the polyatomic ion, then everything else is still balanced, just like we said before. So can we just take this left side and paste it onto the right side like we did before? No. Question?
I was gonna ask, how is that -3 on the?
The charge of phosphate is -3, which is not going to show up over there, because remember, phosphate's a polyatomic ion, and there's that nifty handy dandy little table that tells you the charge of phosphate as opposed to phosphite, as opposed to hypophosphite, right? And that's going to be different than sulfate or carbonate and all of those fun things, and that's just something we just have to remember / know how to look up, right? So, That's where that charge comes from, which is why it takes 3 sodium ions to balance it out, right? That's why it takes, well, hold on, we have 3 magnesium ions here, but we have to have 2 phosphates here. Why is that? Well, because magnesium has a charge of what? Not +1, but +2. So we have a 2 and a 3, and that means we have to go up to 6, right? So, how do we get from here to here? We're going to do this nifty little trick where I put someone in an epileptic seizure by doing this, and then this, and then this, and then this.
Not Trisha.
We can start off with the easiest thing to do. We could just say, well, we multiply. Is that what's happening? Nope, because 3 times 1 is what? 3. Okay, so it's not that. So, our biggest problem child here is our phosphates. Let's start with that. We go from 2, so we need to double the amount of phosphates that are on the left. Which means that's going to double the number of sodium phosphate atoms or molecules that we have right there, right? So what's that going to do? We now have 2 times 3. That gives us 6 sodium atoms. So how many sodium atoms do we need on the right? If we're starting with 6? 6. So why do we put a 6 right there and not something else? How many sodium atoms are in this sodium chloride molecule? Just 1 each, right? So we have to put a 6 there. Right? What? Did I lose you? How many sodium atoms are on the left side of this equation? 6. How do you know? Because there's 3 per molecule, and there are 2 molecules. 2 molecules, 3 each equals 6. Right? That same math happens here. How many sodium per molecule? 1. So how many molecules do we need? 6. Question?
Just making sure, so like the number in front, the 2 and the 3, we multiply those?
Yes, 2 times 3, and also 2 times the orange phosphate.
Got it.
Right?
Yeah. Because I'm trying to remember. Yeah. Because
So-
then the 3 over there, the 3 next to the Mg is multiplied by that 2Cl, and that gives it 6. So then that balances it out. But then, what's the 3 over there? Because then, wait, why
The
did
first teacher I've
Mg
had with
move?
the soundtrack.
What?
Wait,
The
never
first
mind.
teacher I've had with the soundtrack.
I have, yes, not just a theme song, the soundtrack. Everyone deserves a soundtrack, but some people need, or everyone deserves a theme song, but some people need a soundtrack. So, here we go. So this is our 2. This is like, when you're doing an equation, right, where you have like 4x squared y, you remember that from algebra? Right? That means you have 4 of this thing, right? But also 4 of that thing, right? So, if we remember that these elements and polyatomic ions are placeholders for particles, right? So that means that we have 2 times that, which means we have a total of,
6.
right? We also have 2 times that, which is 2 times all of this, which technically means there would be 2 phosphoruses and 8 oxygens, right? But remember, this is a unit. This right here equals X. So if I need to, I could draw this as sodium X. Follow? So, as long as we make sure that we have the same number of X on the left and the right, then we're balanced. Doesn't matter what X is, right? Now, this would be different. This would get much harder if we were going from phosphate to phosphite. What would that be? Instead of PO4, it would be PO3. Now, all of a sudden, now we got to start worrying about oxygens, and it's still not that much harder because it's just phosphate plus oxygen or minus oxygen. No. But yes.
It's kind of, or,
If you can add 2 plus 2, you can also add 222 plus 597, right? Concepts are the same. The difficulty of applying them might require a little bit more thinking on the back end. Theoretically, you should be able to balance an equation even if we are moving from phosphate to phosphite. It is a chemical change that can happen. It does happen. So somebody, somewhere, is going, dang, Herbert, and having to balance an equation with phosphate to phosphite in it. It's not that hard. It might sound hard. But all it means is that we just have to worry about extra oxygen on the right side, right? Because if we do go from phosphate to phosphite, what does that mean? It just means that we have some extra oxygen popping up somewhere else, right? As long as the number of atoms or particles is the same on the left and the right, then we're balanced. So don't get scared. This is simple math. This is just logic puzzles. Did you guys ever do those challenges where it's like, there's 4 chairs and 4 students. Billy has to sit in the first chair, and Susan can't. Did you ever do those logic puzzles? You know what I'm talking about? If you were good at those, this should be easy. Because it's just a logic puzzle. Start with one piece. Okay, how about this? Do you do Sudoku?
Yes.
If you can do Sudoku, you can do this. Find other metaphor for just simple math questions. This is just a logic puzzle.
Did anybody here solve Snape's riddle, first Harry Potter book, along with Hermione Granger? I can talk to you right now.
All right, problem child.
Wait, so
Question, go ahead.
I get how 3 and 2 would be 6, but what about the PO4? That would be 2.
We have 2 molecules of phosphate on the left, right? How many molecules of phosphate do we have on the right? 2. Because there is 1 molecule of magnesium phosphate as a product. That 1 molecule has 3 atoms of magnesium, but it also has both of the phosphate ions that we started with. So we started with 2 phosphate ions, we end with 2 phosphate ions, and so the phosphate ions are balanced. Make sense? Because of that little 2 right there. Kinda? So, when we go through this, it's not just a matter of multiplying products and reactants. Start with 1 and build your way up, and then go back. So here we have, what do we start with? Magnesium chloride. So we start with our sodium. That would make it easy. If we started with just sodium here, then how many of these would we need over here? If we started with just 1 molecule of this guy, how many of these guys over here would we need? 3. 3 sodium here, 3 sodium here, right? So we put a 3. All right, that would give us how many molecules of chlorine? 3. How many do we have over here? 2. Crap. All right, so what do we need to do to put 3 and 2 together? Double both of them, multiply by each other, right, to bring this up? So that means that we now have 6 of chlorine here, but that means we need to put a 6 right there, which means we need to put a 2. Just start stepping through it. Lovely. We get one slide where it does not explain in any way how they did that. So, let's go through this again. So we have 3 sodium right here, right? So I would put a 3 over here. We'll put it down there as a placeholder. This is going to get messy because when I erase this, it's going to leave a thing. But I don't know if the markup on the smartboard will be any better, so we're going to do it this way. So far we're balanced. That means we have 3 chlorines, right? Uh-oh, now we have a problem. We can't balance our chlorines because we only have 2. So what do you have to do? You have to go to 6, right? So, in order to have 6 chlorines, how many molecules of this do we need? 3. But that means we need to change this number, right? So to have 6 chlorines, we need not 3, but 6 right here, right? Everybody follow so far? Lost you already? So we started with this as 3, right? 3 sodium. So I just went over here and put a 3 in front of that. But if we have 3 sodium, I'll back up. If we have 3 sodium, that means we also have 3 chlorine, right? But on the left there's 2. We can't say give me 1.5 of these guys, right? Theoretically we could. So we can do that here. To make it bigger, what do we need? We need 2 of these molecules, right? So, but, well, not 2. If we got 2 of these, how many? We have 4. We need 3. So you put a 3 there, which gives us how many chlorines? 6. So we need to change this. Not from 3, but 6. But now we have another problem. Is our sodium balanced? No. So how many of these guys do we need to get 6? 2. Okay, so now what about our magnesium? We have 3 magnesiums here. How many do we have here? 3. We good? Okay, all right. Over here we have 2 molecules of this. So how many phosphates do we have? 2. Over here, how many phosphates do we have? 2. Is everything balanced? Yes! Now, there's another way that we could do this. Do we want to try it, or do we want to just stick with this and move on? Do we have this, or do we want to try something that involves a little bit more math, but might be easy, maybe? You brave? You want to try it? You want? Okay. Not sure, so yes. All right. Let's do what we just did. Sodium. How many? 3. So how many of this do we need? 3. That gives us how many chlorines? 3. Okay, so how many of this molecule do we need in order to get 3 chlorines? And this time, we can use fractions. So instead of doubling this molecule or tripling this molecule, how many does it take? We need 1.5 of these guys, right? I don't like this example with fractions. It's just going to confuse us. Let's not do that. There are better examples to do this. The reason that's going to get tricky is 1.5 magnesium to get us 3 means that we're going to need 2, so that's not. It's a shorthand. The problem is that in some situations, doing it like that, saying, well, I need 1.5 of this, then you look over here, sometimes that will work and it makes the math easy, but you can't ever write 1.5 molecules of magnesium chloride. So what would you have to do when you were done? You'd have to take all of those numbers and increase them to get a whole number. So you'd have to double your 1.5 to 3, and then you might have to come back and reduce down, because what do you call it, 8/4? We don't call it 8/4, what do we call it? 2, right? So there is a way to do it with fractions or decimals, but that may or may not be easier depending upon what you're doing. What's important, it doesn't really matter how you get to this, which method you use. Just like one algebra question might have 5 different ways to get to the right answer, right? What matters is you got to the right answer. And that you didn't spend 2 hours on it, because if there's more than one of these on your test, you've just used up your whole test time. So, everybody follow that mostly? Yeah. I'm spending a lot of time on this because this is kind of the take-home portion of this whole chapter. If you can't do this, you can't do chemistry. Period. This is something that I am going to put in your homework, because that's half the point of homework, is to give you extra practice, right? It is something that I highly advise we go into the, if not today in class, we go into the practice problems and work through them in the practice problem slide set, right? Because you will need to know how to do this. Even if you happen to not get a question asking you to do this on the exam, which is possible because there's 60 questions per chapter, and not all of them are going to be from this section of the chapter. But if you happen to luck out and not get one of those exact questions on this exam, inability to do that will screw you up on later exams when we're talking about equations and how much of what you get. This is a foundational skill. Do we have that as a little pop-up thing somewhere in here? Core chemistry skill! You have to know how to do this. But the nifty thing about it is, when that question comes up, balance this equation. At this level of chemistry, I'm not going to say, balance the equation of sodium phosphate plus magnesium chloride, and expect you to understand how those ionic interactions are going to exchange in order to create this precipitate and sodium chloride in a solution. Higher order chemistry classes, you might. What happens when you react sodium phosphate and magnesium chloride? Question mark, period. Well, period, double, question mark, and then you answer it. We're not doing that. So that means that balancing an equation is just a logic puzzle. That's all it is. So do not get scared by this. Just start with one and work through. Eventually you'll get to the end, then go back, add everything up again, and make sure that what you have on the left matches what you have on the right. And if you have done that, then you are done. It looks like a lot of work. It's really just a logic puzzle. But it is a core skill. All right. Are we good with that before we move on? We are past an hour, and I need to go get some water in my empty fluid cup. So let's take a 10-minute break, and then we'll power through to the end after that. Everybody good? All right, let's do it.
Chair right there.
Yeah, did it reach out and grab you? 5 till, everybody. Good to see you, Dr. Moon.
Thank you. See you.
Now?
Yeah, right after I went back to work.
Every year I listen to this series. That interesting thought.
Do you watch Tyler do it?
Who?
Tyler do it, like, he's on YouTube, and he shows like step by step.
What's his name?
We use our imagination.
See, I could have gone to get more soda, but I didn't. I just got more water.
So you're claiming it was water before.
Of soda before. At one time, this held an incredibly unhealthy beverage.
Not just BPAs.
All right, so now what was it? I need to do what?
I don't know, I made up a word for it.
Oh shit.
Obviously, don't have access to the structure, but you do it.
Nope, that's not the right button. one downside of having you over here to help you, Christian, is that I can't have you over here to look at everyone else's grades. So, well, give me a second and what? Well, but see, then I can't even change it while you're there. Because I can look at yours. Let's go to quizzes, and see if it's an option on the quiz itself.
Is that thing just so old that they had to write it in?
Had to what? Yeah, to draw it, yeah, to thicken the line. Looks like it.
They actually added, no, they added they added this entire section.
Right. Yeah, drew it in. That means it actually is quite a bit older.
If I did see that, I would
see a way in the settings for the quiz to make it, let's see, submission views. Show questions, no. Add additional views. Okay, there we go, okay, so.
And then I put that tutorial up so people can find it.
All right.
Seem to be the only one using the discussion board.
You are the most prolific user of it, but you were not the only one.
I read some of it.
I've never been told to talk to you. Never, ever.
Show all questions. Show question answers.
Are you figuring it out?
Yeah, I think so.
You do want to use a response.
With that, oh yeah, because that's your answer, isn't it? So I can tell what you said. And if I give it after everybody finishes, so if I use the default view and then manually change it to that view after everyone's done.
Right. Okay. Well, I don't think it'll show in the view until the test itself is.
Until it's closed anyway?
Yeah.
You're right.
But, I mean, that would be something to experiment with.
Is it a fidget spinner?
It is, but it's one I like a lot better. Instead of having 3 lobes that bump on things and shoot out your hand.
Circular.
Yeah. So it's got a nice brass flywheel up the outside. So when I first got it, before it went through the laundry a few times, oops, wow, I can't. It would spin for 8 minutes. And it's also quieter. But, yeah, of course, for hand, it just, yeah, so much. Back during Mo's class, I got a PGQ, and I just didn't get it. Yeah, it's too noisy. If you drop them, they shoot apart in all the pieces. So I kept having less and less parts of my cube that functioned, and more superglue. But this, I don't even notice when I take it out of my pocket half the time. But it keeps you from picking OCD type stuff. Well, it helps. Huh?
I'm OCD. My house is OCD.
Then what's your kids?
My wife is mildly OCD as well, and that's the same thing, which is when I was like, honey, you have children. Your house will not be clean or ordered.
You can't find somebody with OCD. I'm the same way.
Well,
My house is always clean. Always.
right, but it's like, my children, like, so my wife will be gone for an afternoon, and I'll just be sitting at my computer or playing with them or whatever, and then like, all right, at the end of the day, because she comes in, this house is, look at this room, it's a mess. Like, A, it takes 5 minutes to clean it. because we have 3 tubs for all the kids' toys to go into. So, done. Right?
Didn't you
But
think
the
of
problem
it?
is, what she does is she comes in after the first hour of kids playing, cleans it up, then they mess it up again. She comes in after the second hour of kids playing, cleans it up, they mess it up again. She comes in after the third hour of kids playing, they mess it up. Comes in after the 4th hour, and then I look at her and go like, I understand why you're exhausted at the end of the day, because you've been doing way more work than you need to. Wait to the end, clean it up once. I understand this is why it's so hard, but I'm not OCD.
Have you tried the entropy argument on?
No. She has a master's degree in biology, so that would make total sense, but that wouldn't make any more sense than what I just said, because it doesn't matter. This is the thing. It's like telling somebody who has a phobia of snakes, don't worry, this snake can't hurt you. That doesn't matter.
It's irrational.
Because, yeah, an irrational fear is by definition irrational. That doesn't make it bad, it just means that there's nothing you can say to rationally overcome it. OCD is a derangement in the way that it functions differently within the brain. And so saying, why can't you just get over it, is like saying, why can't you just get over your fear of snakes? It doesn't happen. It doesn't help. So I get it. But at the same time, I don't get it. Because I don't have that problem.
I miss the unholy trinity. I don't have Tourette's, but I have
Here,
OCD.
she's not here. See if you can look at your exam.
Don't have Tourette's, but I have OCD and ADD. So I'll clean up a room, and then I'll leave. And I'll come back in half an hour later, and I'm like, I just cleaned this. It's because I had gone back in the room and done something,
I see. And yeah.
destroyed it.
Yeah, that's my wife's issue too. I just cleaned this, don't make a mess. Like,
Why do
the
that?
definition of childhood is making messes. You can't tell
So it's
it-
not just some women, I guess, that maybe a lot of us.
Yeah, well,
I
No, don't get me wrong. If I just cleaned a room too, I hate it. I hate watching my children blow into the room and just tornado it away. I totally get that mentality, but that's why it's like, what I do is I just let go of all that and let them be a tornado until the period of them being in that room is over. Like, okay, we're done playing in this room now. Now we clean up, and that way, when I walk back into the room 10 minutes later, it's not destroyed again, and I can feel like my work was not wasted. I totally get the not wanting to waste your effort and work. It's the extra angst that we put ourselves through by working harder than we need to in order to satisfy an irrational need. That's what I don't.
See, I just can't sit down, like I can't focus on homework
Yep.
if my house is dirty.
You fixed
I
it,
have
Adam.
to clean.
Okay, yeah, I'm looking at yours, yeah.
Adam, it works.
Yep. So I know how to do that now.
So you said we should be able to look and.
Yes, but here's the way you have to do it. And you can follow what I'm sure Christian has on his walkthrough.
Yeah.
But the short version is, you don't go to the gradebook, go to the quizzes page.
So do you think others as children,
Just click back on.
before the
And-
mothers love very popular?
Yeah, load up the exam as if you were to take it again. And then that little down arrow or whatever, where you click on submissions.
You can't do the same thing when it comes to sing a song.
Because if you just click on the assignment, it'll just tell you this is your grade and it took you this long, right? But if you click on the little down arrow next to the assignment after you've loaded the assignment, there's a submission. Click on that, and it'll give you the whole quiz. Now, that would not have done that 5 minutes ago. So I now have a view submissions option where your answers are actually there. So you should now be able to do that. Now the homework one has not had that done yet. Let me go ahead and do that.
Yep.
I didn't have to do that.
Oh, no.
I just went to.
How did you do it?
Went to quizzes. Well, I followed my tutorial.
Yeah, of course.
So click the down arrow next to the exam, to submissions.
So just on the quizzes page instead of loading the quiz first? So you,
Right.
Yeah.
And
So-
then and that gives you your attempts, and you click attempt 1, and then there it is. What?
Oh, it's because we're not on the, you can do it on the computer.
What?
You should, well, I just, his worked. Am I still impersonating you? I think I'm still impersonating you. No, I'm not.
Maybe you just did it for me.
Submission views. No, it wasn't just for you.
I was able to do it.
Oh,
Wait, isn't,
Let me look over shoulders.
Oh, no, it doesn't.
Is it in the atom, doesn't it have the same
Are you done?
protons and electrons that it does?
An atom,
Or is that?
Click on
atoms, yeah, same number of protons and electrons. They have different numbers of neutrons.
Question.
Mm-hmm.
When it comes to like balancing equations, are you gonna like
Okay, so if
kind of always give us the two sides?
Yes.
Sometimes I've seen it where it's just like this and then there's no other side, and so you have to like put it all together like in a balanced way or something like that.
so if
If
one
it-
has
The only way that would happen is if
four
it's a
here,
very
it has
simple
five there,
thing, like what is the equation of the combination of aluminum and sulfur to form a salt?
electrons?
Okay.
Where I told you what the equation is,
Right.
but then you might have to write it out in order
Can
to
I
answer.
draw relating?
So you would write aluminum plus
So-
sulfur equals aluminum sulfur.
But even with that, would
One
you,
shell.
like the exam, you would give us like 4
Need an outer
ways
shell.
to answer that, and then like with the homework, we'd have to like, I guess, type it out.
Maybe, yeah. But even then, I don't like the filling blank answers on homework.
Yeah.
Okay.
This,
Yeah,
this
and that's
shell
one way of
fills
thinking
in the
about it
box.
is
There's two,
how to ask a question
and then
is a good
eight,
way to
there's
limit
8, and then
how you think about something.
for simplicity,
Because if you know that I'm not going to ask you an essay question on the exam,
Right.
then you don't need to be answering essay questions in your head, right? When you formulate questions, that's not the type of question you need to be able to ask. So, given that limitation, yeah, well, the worst that can happen is, I might ask you something and then I give you 4 options. Or I give you something and ask you, is this balanced or false? That type of thing. Or I give you something and leave out one thing and put a blank in front of one element and what number goes here.
Sorry, it's not like a
Oh, my, the true false
I was
ones.
an English major.
Okay.
It was 2. You know what I mean?
Minus
So I
9
think
elements, lithium, sodium,
it's
and
hard
potassium.
sometimes to like get rid of that.
Alright, so I think I have also changed the view on your homework number 1.
Yeah. Depends on the subject. I think that's why I'm better with biology, like I like words.
Well, that was stupid.
I hate that.
And I'll change your homework number 3 to do that once it's closed.
Words, blood, and drugs.
Because evidently it does not, anytime the view is there, it's visible. So if you're looking at it now, which you all are, the exam still hasn't closed until Thursday. But I didn't change that.
But is everybody submitted?
Yes,
Okay, we're fine.
right. But automatic grading or otherwise, it's still something where the default will probably not have it, and then as soon as everyone is submitted, then it will activate. Theoretically, on exams, it really doesn't even matter because the chances that the one person who hasn't had it can, like, they're not going to be able to look at your test to get the answers because 90% of their questions are going to be totally different.
You said
But homework, I'm still probably going to have to keep that
Oh,
as a separate
Secret.
little bit of secret, at least at
I
first.
thought it was like homework is gonna be different for each person.
No, homework is the same. Exams are different for each person.
Ah.
Just now realizing the potential. No, I'm not coming up with 60 different homework questions for you. There aren't that many homework questions in the back of the book, and that's where the questions are coming from. So,
That's just laziness, right?
yeah.
I missed.
Sure.
4 6.
All right, so, as long as it... What?
Can I ask about a question?
Is it about the test?
Yeah.
Not right now.
Okay.
You can either ask after class, or you can send me an email. I can look at your, just, if you double check, you can say, why did I miss check question 13, whatever it is, right? So find the questions that you missed, which ones you think you should have gotten right, and if you're right, then I'll give you points back. If you're wrong, I'll explain why you're wrong. But I'm not going to do that for, quote, every question that somebody missed. But like I said, this is the first time I'm using these test banks. I had to manually add these questions, so it's entirely possible that I did something wrong in importing them all. So that I will not take it personally if you are correct and I graded you wrong. All right, so you should be able to do that now. You should be able to look at your question, test number 1 and homework number 1. And there you go. And if I'm good about this, I'll remember to change the view on homework number, well, 2 will be easy, but like the homeworks that are due right when the tests open, type of thing, I'll open those for you so that you can look at those too. All right, let's talk about 7.5. We're only halfway through this, slide-wise.
You were going really fast, so.
I was, or at least it felt like it at first. Are we halfway through? We got what? 8:55. So we have 2 hours left. That should be enough time. Yeah, that first half went fairly quickly. Types of chemical reactions. So what we're going to try and do here is understand the difference between combination, decomposition. What are you doing? Combination, decomposition, single replacement, and double replacement or combustion. So different categories of reactions. So here's all of those things in bullet points, just in case you want to write them down. So combination reaction is when we're taking 2 or more elements and forming something else. Makes sense? It's as if we are using the appropriate English words to describe the process. A combination reaction is when you combine reactants to form a single or larger product. So here we have magnesium plus oxygen goes to form magnesium oxide, sodium plus chlorine goes to form sodium chloride, sulfite actually, if I understand correctly, if I recall correctly, because sulfate, P and S were fours. Sulfites plus oxygen, or excuse me, water goes to form hydrogen sulfate, which is an aqueous acid. That's this right here is the formula for acid rain.
Awesome.
Yeah. Just make this happen, except instead of H2O liquid, make it H2O gas, or even just H2O liquid as it begins to condense. And you get H2SO4 aqueous in liquid water, in the raindrops, and that's acid rain. Fun stuff. Where would you get this sulfite in gaseous form? Where would that be coming from in the case of acid rain?
Volcano.
What's that?
The volcano.
Volcano is one source. Coal power plants is another one. So, what's happening here? We have this coil of magnesium.
Yeah.
We are burning that coil of magnesium, and it is reacting with oxygen in the air to form a new solid compound, magnesium oxide, which has very different chemical properties from the pure magnesium than it was before.
That's not a great photo, is it? It's got to be made up.
Well,
Because the magnesium is so bright. And the
the-
contrast on the arm holding it hasn't changed.
Well, no, it's on fire.
Right, it'd be so bright, it would white out the camera. You wouldn't be able to see the arm holding it.
I also have a hard time believing that that's actually like photoshopped fire. If it's a really thin wire.
I think it's composite. They took a photo with and then replaced the background.
Maybe. Not really important.
And then
The oxygen is definitely photoshopped in.
they pin the moth to the tree.
Yeah, exactly. Yep. Because moths never stand on trees. All right. Combination reaction. Combining magnesium and gaseous oxygen to form magnesium oxide as a solid. All right, decomposition reaction is a combination reaction in the opposite direction. So a decomposition is when we're breaking something down, right? We're all familiar with what decomposition means, right? The breakdown of something, decomposing material, decomposing leaves, your compost pile in your backyard where you put all of your organic waste instead of throwing it into the big place where we keep all of our waste. I'm seriously. Landfill. Thank you. Big place where. I was like just picturing the little like loading, like nope, just not there. Decomposition. So we take our reactant A, which is a little bit of a misnomer, but they've done it. So reactant A, which is both A and B together. In this case, mercury oxide or potassium chlorate. And we are breaking them down to form liquid mercury and gaseous oxygen, or solid potassium chloride and gaseous oxygen. Either way, a decomposition reaction is a reaction where you are taking one molecule and breaking it down into multiple molecules. Easiest and most common decomposition is 1 into 2. 1 water into 1 reactant into 2 different products, right? Which does not mean that there will always be a 1 in front of that. Remember, we have to balance these things, right? So, a decomposition reaction where we take mercury oxide, mercury 2 oxide, we add a little bit of heat, and because of that additional heat, we break the bonds between the mercury and the oxygen, and we get liquid mercury as a metal, and gaseous oxygen evolves from that. Which is what those bubbles up here are. Bubbling up, release the gas. Single replacement, also appropriately named, where we take 2 different reactants and we are replacing one part of one of those reactants with the other. So A plus BC as a compound goes to form AC as a compound, leaving B off by itself. So zinc as a solid plus hydrochloric acid goes to form zinc chloride and hydrogen gas. Iron plus copper sulfate as an aqueous solution goes to form iron sulfate and copper as a solid. So what's happening here is you take an aqueous solution, put in a little bit of iron dust, and the iron dust is, let's use the right term here. The iron dust is reacting with the copper sulfate ions. And it is, through redox reactions, it is gaining electrons from the copper so that it is now an ionic state. Or losing electrons, actually, to the copper, so that it is now an ionic state. The copper reaches a solid or a steady state, and therefore it precipitates out as a solid. So we are replacing iron, solid iron, and it will look like it's dissolving into solution. And at the same time, copper will begin appearing out of solution. Question?
So, okay, so, like, if this were on a test, we would just show us like ABC and then turn this into like an ACE, like a CAB, whatever that is.
Mm-hmm.
Would you just like show us that and like have that equation out and then we'd have to like fill that part in?
Well, there's a lot of things that I could do with something like this if I use it as a picture type of thing. I could ask you what type of reaction is this, and the answer obviously would be a single replacement. I could ask you what, I could like leave a blank in front of this thing right here and ask what number goes there, right? I could even conceptually leave a blank here and a blank there and ask you what numbers go there, and then you just have 4 options to choose from, right? But yeah, more than likely it's going to look like, if it's a matter of what type of reaction is this, it's going to look like this.
Okay.
Now I could also give you this reaction right here drawn exactly as that is and ask you what type of reaction is that. Because all you have to do is look, zinc plus hydrochloric acid is zinc chloride, so what's happening here? We're swapping out zinc for hydrogen. What is that? Single replacement, right? Or I could do the A and BC. Zinc plus hydrochloric aqueous solution goes from hydrogen and zinc chloride. So if you add zinc to hydrochloric acid, it bubbles and the zinc dissolves. What's happening is that the zinc is gaining, or I should say losing electrons, and therefore becoming an ion and forming ionic zinc chloride in solution. But if zinc is losing electrons, Zn, if zinc is losing electrons in order to come down to, as most metals do, emptying its outer shell, where are those electrons going? Those electrons that zinc is losing is being given to the hydrogen ions in hydrochloric acid. And those hydrogen ions are then combining to form H2 as a gas and bubbling out of solution. Now that's a little bit ahead of the box, if you will. Like if it's just a matter of what type of reaction is this, zinc plus HCl goes to form ZnCl, so the lone guy is pairing up, is cutting in at the dance, if you will, with one of these two guys, right? And so this is a single replacement. What's really happening here is what I just described. When you add zinc and hydrochloric acid, or zinc into hydrochloric acid, what's happening is there is an electron exchange between the zinc and the hydrogen, where zinc is becoming an ion, and the hydrogen is accepting those electrons to stop being an ion and become a gas. That's the chemistry behind why when you put zinc into hydrochloric acid you get bubbles. That's the hydrogen being released. It's not the zinc dissolving. The bubbles aren't from the zinc dissolving. The bubbles are from the hydrogen becoming a gas and bubbling out. But where do you see all the bubbles starting? Why don't we see bubbles beneath, on the bottom end of this little filament of zinc in this solution? Because hydrogen is not forming everywhere in solution. Where is the only place it's forming? Where it's in contact with the zinc. Where zinc and hydrogen can swap electrons. That's why we see bubbles right there, and then the bubbles rise. A single replacement reaction. Because the zinc and the hydrogen ions are exchanging electrons, changing state, and therefore changing chemical properties of where the zinc is, from physical to aqueous. Alright, so if you can have single replacement, then you can have double replacement, right? Triple. Or even triple, quadruple. No. You could have a reaction that is exceptionally involved, that involves the swapping of all sorts of different things. And most chemical reactions are actually multi-stage reactions. So for example, when you take wood and burn it, you get, or sugar and burn it, which is what wood is, you get CO2, H2O, and energy. But that whole reaction takes about 12 steps. We sum it up by saying sugar equals CO2, H2O, and energy. But that's 12 different reactions, where this thing's over here and over here, so we get rid of them and add the two equations together. Adding chemical equations, I don't know if we're going to get into that in this book or not. That's like a subsection type of subject. I'm not sure if it's going to come up. So here we have silver nitrate and sodium chloride turning into silver chloride and sodium nitrate. Double replacement. We're both cutting into each other's dance partners. Sodium sulfate as an aqueous solution, barium chloride as an aqueous solution. You combine them at this point where it's dripping in, and you see this, it's kind of hard to see, but there's a white cloud forming right there. That's the barium sulfate. Barium sulfate cannot, at least under these conditions, is not aqueous, does not dissolve, and therefore it precipitates out as a solid, and we're left with sodium chloride in solution. Now something that's a little bit ahead of the box here, we're talking about a lot of these replacement reactions that we're talking about, you'll note are happening in aqueous solutions. Is this sodium chloride here actually a molecule in an aqueous solution?
No.
When we talk about salt as a molecule, we talk about crystal salt, table salt, that hard stuff, right? But when you add it to water, what does it do? It dissolves. It's not sodium chloride anymore. Really, it's sodium positive ion plus chlorine negative ion. We call it sodium chloride as an aqueous solution because that's shorthand. It's a shorthand way of writing it. But these ionic compounds, when they go into water, they don't stay as a compound, they dissolve. So really what we have is sodium ions, sulfate ions, barium ions, chlorine ions, all four of them together. But we started with two different solutions. When they combine, it just so happens that barium and sulfate like each other so much that when they start dancing, they get tired really quickly and have to get off the dance floor. And they precipitate out as a solid. They can no longer dissolve. Sodium chloride, on the other hand, they can keep dancing. Free-handed, out on the dance floor, doing whatever they want. Because they're still just ions in solution. Once again, half of that discussion is ahead of these slides. The point of a double replacement is when we have two compounds and they're swapping dance partners, both of them, it's a double replacement, right? Combustion reaction. A specific type of reaction where we take carbon-containing compounds and we burn them in the presence of oxygen gas. Where is combustion reactions happening? How could